Hello students, in this video we'll introduce the idea of continuity of a real valued function at a point. We say that y equals f of x, which is a mapping f maps r to r, it's a real valued function, is continuous at a point x equals a if three things are true. If 1, f of a exists. 2, the limit as x goes to a of f of x exists. And 3, not only does the limit exist, but the limit has to be equal to f of a. Now, oftentimes you'll see conditions 2 and 3 combined because if you write down this condition 3, it automatically implies that the limit has to exist since f of a exists. But let's be a little bit pedantic about it and just say that I need the function has to be defined at the point a in question, and the limit as you approach the point a has to exist. And not only that, but it has to be that value, that limit value has to coincide with the value of the function at that point. Okay? Now, there's a more formal way of defining this. So more formally, so here's a more formal definition, more formally. For every epsilon greater than 0, there is delta greater than 0, such that if x minus a is less than delta, this implies that f of x minus f of a is less than epsilon. Okay, that's the formal definition of continuity. We're going to focus more on just using these limit definitions over here because we're very comfortable with limits now. And so let's see some examples of how functions can fail to be continuous. So for example, you can fail to be continuous by not being defined at the point. Here's an example of that. If I look at this function over here, f of x, which is x squared minus 1 over x minus 1, well, what does this function look like? Well, if you were to factor the numerator, this would be x minus 1, x plus 1 over x minus 1, and we have this what's known as a removable discontinuity over here. So this function, as it's defined, is not defined at 1. So note for this function, f of 1 does not exist as it's defined over here, okay? And so if we were to look at this graph, what will happen is, of course, if we could cancel this out, we would just have that f of x is x plus 1 as long as x is not equal to 1. So the graph would look like this. Here's x, here's y, and then this graph over here, and here's the point x equals 1. So we're going to start over here with a y-intercept of 1. And then the line goes like this. But then when we get to 1, there is a hole, and it goes like this. So that hole over there is a discontinuity. So this is a discontinuity. Because the function is not defined at the point 1. However, if I look at this function over here, g of x, which was, now of course, what should it be? It should just be equal to 2. I can look at I can define g of x to be f of x for x not equal to 1. And I can define g of x to be equal to 2 if x is equal to 1. Now this function, if x is equal to 1 rather, not x equals 2. That's the value. So if x is equal to 1 over here, x equals 1. Okay? Now you can show that this function g is continuous at x equals 1. F is not continuous. This function f is not continuous at x equals 1. Okay? You can also have the limit failing to exist. The other method, the other way by which these functions cannot be continuous, example, the limit can fail to exist. Okay? And what's an example of this? Let me define a function h of x to be equal to x if x is less than 0. And then it's going to be 1 plus sine of x if x is bigger than 0. Okay? Now this function is not continuous at x equals 0. And let's prove that. Well, let's compute the limit as x goes to 0 from the left. That means x is less than 0 in this case of this function h of x. Well, if you're less than 0, the value of your function h of x is just equal to x. So this is just going to be the limit as x goes to 0 from the left of x, which we know to be equal to 0. That limit is 0. However, if we look at the limit the other way, if I look at the limit as x goes to 0 from the right, which means that x is greater than 0, our function h of x now becomes 1 plus sine. Since the sine of 0 is equal to 0, this limit is just equal to 1. So the limit from the left is not equal to the limit from the right, so the limit fails to exist. So this limit over here does not exist, so the function is not continuous at the point 0. So we have two different sort of mechanisms by which a function cannot be continuous. The function value cannot exist, so I can have a hole or maybe an asymptote even, and it can fail to exist by the limit failing to exist. So those are the two ways in which a function can fail to be continuous. In other words, if I was able to just sort of, we want to think of a continuous function as just at a point of continuity, the limit has to, from the left and the right, have to exist, and they have to coalesce at that point. And that's the intuitive geometric idea behind what continuity is. Thank you very much.